Hi, having discussed what is limit and what is a continuous function, now let us see some properties of continuous functions defined on closed and bounded intervals. So far we were dealing with continuous functions which are defined on some arbitrary subset of real numbers, but in this session we will be discussing the continuous functions which are strictly defined on closed intervals, closed bounded intervals or subsets of real numbers. So, the first definition that we have to look again is that of bounded functions, which already we have discussed in one of the previous sessions. Let A be a subset of R, and if f is a function from A to R, then f is bounded on A if there exists a real number m such that modulus of f of x is less than or equal to m for all x belonging to A. Now, why do we need this restriction modulus of f of x less than or equal to m is that we have the function something like this. You have your x belonging to A subset of R, x is somewhere here. The function f should be bounded, means it should not go, or the image or the values of the function should not exceed indefinitely or should not drop down indefinitely. So, there should be some restriction for the function, and the function should lie entirely in this interval. So, we do not know the shape of the graph or shape of the function, so we can draw some arbitrary function in between, but since the function is to be bounded, we need to restrict the function between two values. So, that is why we have some value, say c less than or equal to f of x less than or equal to some d for every x value. And generalizing this concept, we are taking some negative m less than or equal to f of x less than or equal to capital M, which leads to the definition modulus of f of x less than or equal to modulus of f of x less than or equal to some number m. So, that is why for the bounded functions or boundedness of a function, we are restricting the function to be taking the absolute value less than or equal to some real number capital M. So, with this definition, we can look at what is the condition given for continuity or continuous functions. If I is a closed bounded interval and f is a function defined from I to R and it is continuous throughout the interval I, then definitely f is bounded on I. So, the proof goes like this. We can look at the proof. We are given that the function f is defined on a closed and bounded interval. So, we can write this I as some closed bounded interval, say a b. So, f is defined from closed interval a b to R. To show that f is bounded on I, and given additionally f is continuous. F is continuous throughout the interval I, we have to show that f is bounded on I. So, to show something is true, we will assume, that is a technique used in mathematics, we will assume the converse or contradictory. If possible, let f is not bounded or unbounded on I. Unbounded on this interval. So, what is the meaning of this unboundedness? Therefore, for every natural number n, there exists a value, say xn, belonging to the interval I, such that your f of xn will be greater than n. Why? Because by assumption we have made our f to be unbounded. So, f is unbounded means corresponding to any natural number you take, there definitely exists at least one value in between a and b or in the interval I, such that the image goes beyond that natural number. So, name it as equation number 1. And where does this sequence xn belong to? So, corresponding to every natural number we have a point. So, corresponding to 1 we have an x1, corresponding to 2 we have an x2, corresponding to 3 we have an x3. So, we have created a sequence xn. We have a sequence xn in I such that your f of xn is greater than n. So, that is our condition number 1 in another words. So, because this sequence xn is a sequence in I, we have sequence xn is a sequence in the closed bounded interval AB, which indicates that sequence xn is also bounded. Because this a and b are finite values, I is a closed bounded interval, we have our sequence xn to be bounded. So, this shows that we have studied a result for bounded sequences. We have learned a result that every bounded sequence has a convergent subsequence, which is called the Bolzano-Weierstrass theorem. So, by Bolzano-Weierstrass theorem, sequence xn has a convergent subsequence, say sequence xnr. So, we have now sequence xn has a convergent subsequence, say xnr, where xnr, because it is a convergent subsequence, we can say limit nr tends to infinity, xnr is equal to some number, say f of x. So, we have your sequence xn, which is a sequence in AB having a convergent subsequence. So, because sequence xn is a sequence in AB, every point of xn has an image, because f is defined from I to closed interval I to R. Given f is continuous, given f is continuous on I, which means if we have a neighborhood of any point or a neighborhood of the limiting point, we have the corresponding image also going to the neighborhood of that limiting value. So, that is called the sequential criteria for continuous functions. We have learned limit x tends to c, f of x is equal to f of c. Likewise, because your xnr's are going very close to x, the corresponding images will be going to the epsilon neighborhood of f of x. So, we have whenever xnr converges to x implies f of xnr converges to f of x. This is called the sequential criteria for continuity. Criteria for continuity. That actually follows from the definition of limit of a sequence, and using the concept of continuity we have this. So, now we have the corresponding images, or for every nr there is a corresponding xnr, and corresponding to every xnr there is an f of xnr. So, we have this sequence XNR is a subsequence, means for each XNR your f of XNR is also a sequence which converges to the number f of x in R, or f of x which is a real number. So, by the concept of convergence of real sequences, we have learned that every convergent sequence is bounded. So, we have f of XNR is a converging sequence, means f of XNR as a sequence is bounded, because it follows from the theorem convergence implies boundedness, which we have learned in the case of real sequences in the previous sessions. So, f of XNR is bounded now, but by the definition or by the assumptions that we had in the previous statements that we have made, XNR is a sequence in AB such that f of xn is greater than n. And this XNR, where does it come from? It is a subsequence of this xn. So, if you have a sequence xn, namely something like this, if you have a sequence x1, x2, etc., the subsequence may be something like starting from x5, x7, x9, x8, x11 or x10, like that. x8 cannot come after x9. So, x10 and so on. So, we can see the corresponding suffixes or the corresponding n and nrs are such that nr is greater than n for every n. So, you have your xnr such that f of xnr is greater than nr, or which is greater than n, because your f of xn by assumption was greater than n. So, this follows from the result that f of xn is greater than n. We have established by our assumption that f is unbounded. So, f of xnr becomes greater than nr, and this indicates that our f of xnr cannot be bounded. But that is a contradiction, because we have our f of xnr to be a convergent sequence, and hence our f of xnr should be bounded. So, we arrive at a contradiction. So, all our assumptions in the previous cases are wrong. So, f should be bounded. Therefore, f is bounded. So, this is a contradiction. Therefore, f is bounded. So, that completes the proof of the first result, namely, if I is a closed bounded interval and f is a function from I to R which is continuous on I, then f is bounded on I. So, that is a very important theorem that you have to learn. The next important result is the main result of this section, which is called the maximum or minimum theorem. And before going to the maximum minimum theorem, we will see what does absolute maximum or what does absolute minimum mean. So, this is the definition of absolute maximum of a function. Let A be a subset of R, and if f is a function from A to R, then f is said to have an absolute maximum on A if there is a point alpha in A such that f of alpha is greater than or equal to f of x for all x belonging to A. So, remember that the point can be named in any letter. It is a representative letter, it is alpha written here. You can use any representative letter, but remember that for a function to have an absolute maximum, there should be at least one point in the domain where the function takes that value or attains that value. That is the main importance of this definition that you have to keep in mind. The function should take that maximum value at some point on the domain. So, f is said to have an absolute maximum if there is a point alpha in A such that f of alpha is greater than or equal to f of x for all x belonging to A. Similar is the definition of absolute minimum, which says that there should be a point beta in A such that f of beta is less than or equal to f of x for all x belonging to A. So, again the minimum should be attained at some point beta in the domain. The function should take the value f of beta, then only we will say that it is a minimum. Otherwise, we will call it simply as a supremum and an infimum. So, the main difference between maximum and supremum and minimum and infimum is that infimum and supremum need not belong to the set, or infimum and supremum need not be attained by the function, but maximum and minimum are the values which are to be attained, which should be attained by the function. Then only we will call it the maximum and the minimum. And if a maximum exists, the supremum is exactly same as maximum, and if infimum or if minimum exists, infimum is exactly same as the minimum, because we are defining what is absolute maximum and absolute minimum. There is some other definition of maximum and minimum which is called local maximum and local minimum, which is a different concept. We are looking at only a small neighborhood in the domain where the function takes a maximum and function takes a minimum. Then it is called a local maximum and local minimum. This is absolute maximum and absolute minimum. Now comes the important theorem, which is called the maximum minimum theorem. Again, we have I defined, or I is defined as a closed bounded interval. That is why we are taking I to be some closed interval a b. F from I to R is continuous on I, then f surely has an absolute maximum and an absolute minimum on the interval I. So, this is called the maximum minimum theorem. So, we can look at the proof. The proof goes like this. Proof of maximum minimum theorem. Goes like this. Given, we will start with what are the given conditions. Given f is defined on some interval I equal to closed a b to R, and f is continuous on I. So, just previously we have learned a result for the same sort of function. If f is defined on a closed bounded interval and is continuous, definitely f is bounded. So, these two conditions indicates that f is bounded. So, by the definition of bounded functions, we know, therefore, the set f of x such that x belongs to I, which is called the range set, is bounded. And where does this range set belong to? The range set is a subset of the set of all real numbers. So, now we have a bounded subset of R. The set f of x is a bounded subset of R, and which reminds us of something that we have studied earlier. For a bounded subset of R, or if a set has an upper bound, definitely it has a supremum in R, and if it is bounded below, it definitely has an infimum in R. So, by completeness property that we have studied in one of the previous cases, completeness property of R, by completeness property of real numbers, this set f of x has a supremum and an infimum in R. So, let us denote the supremum and infimum by some numbers. Say m is the infimum of this set f of x, and capital M we are going to define as supremum of f of x. Okay, so far so good. So we have defined capital M to be the supremum and small m to be the infimum. So the image set has a supremum and an infimum. Now we need to show that these are the maximum and minimum that we want to or we intend to show. So our claim is that we are going to show that this capital M is the maximum and small m is the minimum. So by the definition of maximum and minimum, we have to show that there is some point on the interval I which takes the function to this value capital M, and there is some point in the interval I which takes the function to the value small m also. Then only we will be able to show that these are the maximum and minimums that we are expecting to prove. So how to get into that? So we have, yes, so we will start with the supremum of f of x. So since capital M is the supremum of f of x, for every n, capital M minus 1 by n cannot be an upper bound. Why? Because m minus 1 by n is definitely less than m, and because m is the supremum or least upper bound, m minus 1 by n cannot be an upper bound of this set of f of x. So that shows that there exists some point xn in I such that m minus 1 by n is strictly less than f of xn, which is less than m. Now why does this condition hold? Because m is the supremum of f of x. So definitely m minus 1 by n is not an upper bound, shows that there is some number xn in the interval I for which f of xn or the image is greater than m minus 1 by n, and that is definitely less than m, follows from the supremum. So this is true for every n. So we have got a sequence xn in I. So sequence xn, because for every n we have a corresponding xn. So for sequence xn in I, as we had seen in the previous case, since I is closed and bounded, this is bounded. Therefore, by Bolzano-Weierstrass theorem, this sequence xn has a convergent subsequence, say xnr, sequence xnr, which converges to some number say x, or which converges to some number say alpha, we can say, which converges to some number say alpha. Okay. So xnr definitely has a limit. Now xnr is in I, and I is not only bounded, it is closed also. Now what is the peculiarity of closed sets? Whenever you have a limit, that limit should belong to the set. That is the meaning of closed set. So since xnr converges to alpha and sequence xnr is a sequence in I which is closed. So a closed set means a set having all its limit points or all its cluster points, we can say, and hence alpha belongs to the same set I where these xnr also belong. So alpha belongs to I. Now by continuity of f, f of xnr should go to f of alpha, since we have seen the sequence xnr goes to alpha. So, XNR goes to alpha means f of XNR goes to f of alpha by the sequential criteria that we have seen in the previous case. So, XNR goes to alpha means f of XNR goes to f of alpha. Also by our assumption or by our proof statements, we have f of or m minus 1 by nr is less than f of xnr less than capital M, because we have already seen m minus 1 by n is less than f of xn less than m. So, we can replace n by nr, there is no problem. We have m minus 1 by nr is less than f of xnr less than m. So, as nr goes to infinity, what happens to this term? It will go to 0. So, f of xnr goes to m by sandwich theorem that we have seen in the previous case. This side goes to m, this side goes to m. So, the middle sequence also goes to m. So, f of xnr goes to m. So, in the previous slide we have seen f of xnr goes to f of alpha, and now we have seen that f of xnr goes to m. Therefore, your f of alpha should be exactly equal to m, because there cannot be two limits. The limit, if it exists, should be unique. And so, we have proved that this capital M, which was supposed to be the supremum, is attained at some point alpha by the function. So, which shows that f of alpha is the maximum value or absolute maximum. Similarly, we can show it is attained by a minimum, or minimum is also attained by taking small m plus 1 by n, because it is not the supremum, it is the infimum that we are taking. So, we will consider the same case, exactly similar case, by taking small m plus 1 by n, and that lies between small m and m plus 1 by n. So, that part I am not going to prove here, it is left as an exercise. Okay. So, that is the absolute maximum and minimum theorem, which is a very important result, and we can see some examples of continuous functions which attains the maximum and minimum, which are the sine functions and cosine functions. Maximum of sine function is 1, minimum is minus 1, and maximum of cosine function is 1 and minimum is negative 1, and that is why we always write negative 1 less than or equal to sin x less than or equal to 1 for every x belonging to R. So, throughout the entire real line, these functions are functions which assumes the maximum and minimum throughout the entire real line. That is why it is the entire graph lies between the values 1 and minus 1. So, this is an example of a function which attains the maximum and minimum, and that is all regarding maximum and minimum of continuous functions, and thank you.